Page 4 of Applications of Calculus Kinematics. Number 7, a particle P moves in a straight line. Its displacement from the origin O is given by this function, something new, exponential function, where t is the time of seconds, t is always positive. Find the velocity and acceleration functions. Okay, this is pretty regular business now. We're going to find the velocity function by taking the first derivative of the s function. We're going to find the acceleration function by taking the second derivative. So let's take the first derivative of the function they gave us. Derivative of 100t, of course, is just 100. Just remove the t. Derivative of 200e to the negative t over 5 is 200e to the negative t over 5, chain rule, multiplied by negative 1/5. Simplifying, 100 plus 200 200 divided by 5, right? Which would be, and also negative. So I'm just going to put negative 200 divided by 5 would be 40 e to the negative t over 5. So that's our s dash function. Our s double dash function would be the derivative of that. The derivative of 100 is 0, of course. The derivative of negative 40 e to the negative t over 5 would be negative 40 e to the negative t over 5, chain rule, negative 1/5. So that would be 40 divided by 5 would be positive 8 e to the negative t over 5, right? Because 40 divided by 5 is 8. So that is the acceleration function. B, find the initial position, velocity, and acceleration of P, the initial conditions. So we want to put t equals 0 into s, v, and a and see what we get. So s of 0 is equal to 100 times 0 is 0. 200 e to the 0 is just 200, right? So s of 0 is 200. V of 0 is, we're just going to put 0 into here, so 100 just stays 100, minus 40 e to the 0, which would be minus 40, 60. So the velocity is positive 60. And acceleration function would be, I'm going to put 0 into here, so it would be 8 e to the 0, which is just 8. So that is the initial conditions of position, velocity, and acceleration. So it is located on the right side of the origin, it is moving to the right, and the acceleration is also to the right initially. Discuss the velocity of P as t approaches infinity. So let's look at the velocity function again. The velocity function is 100 minus 40 e to the negative t over 5. They want to know what happens to the velocity function as t approaches infinity. Notice that the infinity would happen here. E to the negative infinity is basically 1 over e to the infinity, or 1 over a big number. It would eventually approach 0, right? So like basically what happens is this expression goes to 0, and what you're left with is 100. So the velocity would approach 100 as t approaches infinity. Sketch the graph of the velocity function. So let's do a sketch. We know that the velocity function has a asymptote at 100, which the function is going to approach as t approaches infinity. Where does it start out? Remember that at the beginning the velocity starts out at 60, so the y-intercept would be 60. That is the sketch of the velocity function. Find when the velocity of P is 80 centimeters per second. That looks like it would happen about here. Let's find that using the function 100 minus 40 e to the negative t over 5 is equal to 80. Is that right? 80. And let's solve that. So subtract 80 from both sides. We'll have 20 on the left side. So add 40 e to the negative t over 5 to both sides. We'll have that on the right side. Divide both sides by 40. We'll have 0.5 equals e to the negative t over 5. take the natural log of both sides, natural log of 0.5 equals negative t over 5. Multiply both sides by negative 5, we'll have negative 5 natural log of 0.5 equals t. And then if we want to know exactly what that is, or what that is close to, not exactly, but negative 5 natural log of 0.5, it's equal to 3.47. So the t value is 3.47. That is when the velocity is 80 centimeters per second. All right, let's look at integration used for kinematics. Notice that up until now we were just taking derivatives. They give us the s function. We took the first derivative, we got velocity. We took the second derivative, we got acceleration. Now let's see how integrals can help us with kinematics. Write the integral that calculates the area under the velocity curve, which also finds the distance traveled. Okay, remember that when we take derivatives of the s function, we get velocity. When we take another derivative, we get acceleration. What if we go backwards? If we went backwards, what is the backwards version of derivatives? It's integrals. So if we take the integral of a, we'll get v. If we take the integral of v, we'll get s. So in this case, we have v. So if we do the integral of v, we would get s, right? So displacement equals the integral from t1 to t2 of the velocity function integrated over the variable t. All right. Number 1, a runner has the velocity time graph shown. Find the total distance traveled by the runner. Well, if we want to find the total distance traveled by the runner, what we're going to do is we're going to integrate from 0 to 20. And we're going to find basically the area under this curve. Now they didn't give us a function, but we can easily find the area under this curve, right? So what is the area under this curve? Well, first thing I'm going to do is I'm going to count all the whole blocks. So 1, 2, 3, 4, 5, 6, 7 whole blocks. So there's 7 whole blocks. How many triangles are there? There's this triangle, which is 1 by 3. So half of 1 by 3. So the base is 1. The height is 3, and we're going to take half of that, which is 1.5. Okay. What about this one? This triangle is 1 divided by 2, so it's 0.5. And finally, this triangle here, 1 block wide, 3 blocks tall. No, it's 4 blocks tall. 1 block wide, 4 blocks tall, which would be 4, and then half of that would be 2, so that would be 2. Okay. Then we add up all these blocks. 7 plus 2 plus 2 is 11. So there's 11 blocks total. Now one thing we have to notice about these blocks is the blocks are actually 5 units wide and 2 units tall, right? So each one of these blocks is actually worth 10 units. And so when we take our 11, we need to multiply the 11 by 10, and we'll get 110 meters. Okay, and so actually the distance traveled is 11 times 10, or 110 meters. All right, that is the total distance traveled. All right, now number 3, a cyclist rides off from rest. Rest means he was standing still, accelerating at a constant rate for 3 minutes until she reaches 40 kilometers per hour. She then maintains a constant speed for 4 minutes until reaching a hill. She slows down at a constant rate over 1 minute to 30 and then continues at this rate for 10. At the top of the hill, she reduces her speed uniformly and is stationary 2 minutes later. Draw a graph to show the cyclist's motion and how far has the cyclist traveled. Okay, so let me try to do a graph of that. This graph is describing a velocity graph, kind of like this one, okay? And let's see, there she's going to go for 3 minutes, and then she does 4 minutes, and then 10 minutes. So I think, and then she's stationary for 2 minutes or something. So maybe like I'll make the scale to be 10 and 20 minutes, and looks like the top speed is about 40, maybe. Okay, so at the beginning, the cyclist is still, so it starts at velocity of 0. Accelerated at a constant rate for 3 minutes until she reaches 40. So until 3, she's accelerating at a constant rate until she reaches 40. So it would look kind of like that, right? Then she maintains a constant speed for 4 minutes until reaching a hill. So 4 more minutes would be like until 7. Constant speed would be flat at 40. She slows down at a constant rate over 1 minute to 30 kilometers an hour. So she's going to reduce speed over 1 minute from 7 to 8, okay, at a constant rate. So that's a straight line. Then continues at this rate for 10 minutes. Okay, so 10 minutes would be up to 18. Same speed, 30 kilometers an hour for 10 minutes. And at the top of the hill, she reduces her speed uniformly in a stationary 2 minutes later. So for 2 minutes, she slows down and stops. Okay, so there's a graph. How far has the cyclist traveled? So in order to calculate that, what we need to do is find the area. So I'm just going to divide it into a few blocks. So there's a triangle, there is a rectangle, there is a little triangle and a little rectangle, and here is a big rectangle, and here is a little triangle. Okay, so if we're going to figure out how far the cyclist has traveled, so for this triangle here, it is 3 wide and 40 tall, so 120, but it's half of 120, so it'd be 60, right? This one here is 4 wide and 40 tall, so that's 160. 4 wide and 40 tall. And then this little triangle here is 10 tall and 1 wide divided by 2. So it would be 5. And this rectangle here is 1 wide and 30 tall, so it would be 30. And then this rectangle here is 10 wide and 30 tall, so that would be 300. And then this triangle here is 2 wide and 30 tall, so it's 60 divided by 2, which is 30. Okay, so let's add these up. 60 plus 160 is 220, 250, 255, 555, 585. So 585. And what are the units here? So this is in kilometers per hour, and this is in minutes. Is that right? Okay, so that's a little confusing. So basically our 585 is kilometers per hour times minutes. Okay, and so let's see, how far has a cyclist traveled? In order to figure out exactly how far they traveled, we're going to have to adjust either hours to minutes or minutes to hours. I think it's easier to adjust the hours to minutes, so we'll change hours to 60 minutes. And then we can cancel out the minutes. So if we do 585 divided by 60, that would give us the number of kilometers. So 585 divided by 60. So actually he traveled 9.75 kilometers. Okay? All right. Displacement and velocity functions reading. Since the velocity is equal to the displacement's derivative, S of t can be found by the reverse process by taking the indefinite integral of v of t. Okay, so the integration constant determines the initial position. The initial position. The initial position. Now, the integration constant isn't necessarily the initial position. Sometimes it is the initial position, but the integration constant does determine the initial position. Okay. The definite integral of v of t between t1 and t2 would find the change in displacement between t1 and t2. Okay, so how does that work? We would have an integral of v of t. It would be taken between t1 and t2, and if we did this integral, it would tell us how much the displacement changed between those two times. Okay, basically it is the calculus version of this process we did here, where we basically calculated the area under the curve between two times, and that actually gives us the distance traveled. Okay, that's it for this page.